Hello and welcome. In this question, we're going to be looking at Newton's first law of motion. First thing that we have to do is state Newton's first law of motion. Now, I've told my students in the past that I like to think about Newton's first law of motion as objects don't accelerate on their own, because then it kind of makes the other laws make a little bit more sense. But usually we think about that as objects maintain their current state of motion in a straight line, not accelerating until some outside force is acting upon it, right? So objects at rest remain at rest, objects in motion remain in motion in a straight line until some net force, some resultant force acts upon it. So let's just say objects maintain their current state of motion. That means if they're at rest, they remain at rest. If they're moving with constant velocity, they keep moving with constant velocity. They don't change their direction. They don't accelerate. They don't speed up or slow down. So objects don't accelerate on their own, right? Resultant forces are needed to do that. Objects maintain their current state of motion unless a resultant force acts. Something like that. We'll check the mark sheet, see if we give ourselves the mark for an answer like that. A skier is pulled in a straight line along horizontal ground by a wire attached to a kite as shown. Okay. We're then told that the mass of the skier is 89 kilograms. The wire is at an angle of 28 degrees to the horizontal. The variation with time t of the velocity v of the skier is shown in figure 2.2. So it looks like the skier starts at a speed of 2 meters per second, changes the speed to 4 something after a few seconds, and then keeps that speed there. Okay. Use the figure to determine the distance moved by the skier from the time t equals 0 to t equals 5. So the distance moved is the area underneath this curve, right? That's the displacement. Moving in a straight line. We could break this down into like there's a rectangle down here, and I guess that would be like a trapezoid on top, or there's maybe like a number of ways to sort of break this down. We could think about it as sort of like there's this part of the motion here at 3 seconds. There's this constant speed of 4.2468. So the scale on the y-axis is every square is 0.2. So this is actually 4.4 meters per second. That's sort of the top speed, and it began at a speed of 2 meters per second. So there's this accelerated part of the motion, okay, where the object, the skier is accelerating, right, picking up speed. So there's some ground covered from that. But then there's this, that's just constant speed. So the displacement here is kind of easy. It's just distance equals rate times time, distance equals velocity times time, and the velocity is 4.4, and they were going 4.4 for 2 seconds. So it's not like you don't plug in 5 because they weren't going that long for all 5. That'll be the area underneath sort of that curve. This is just 4.4 meters per second from 3, 4, 5 for 2 seconds. All right, so the units also show meters per second times seconds cancels. We're in meters of displacement. If you can sort of follow that, 4.4 times 2 is 8.8 meters. That would be the displacement, just this part of the graph. This part here then is the accelerated part of the motion, and we could think about it as, well, the displacement is just the initial velocity times time. That's the area of this part of the curve, right? The initial speed times this time, plus the 1/2 at squared. So this is your equation of motion that comes from taking the area underneath sort of a curve like this. We derive this equation by considering a graph just like this. So remember that the v minus u here is the same thing as at. So like the base here is at, the height is t, 1/2 base times height, and so that's how we sort of get this. Because acceleration is v minus u over t, then the difference between sort of this velocity final and this velocity initial is the same thing as at, right? V minus u equals at. So that's why I can say, well, this is v minus u is this height, but it's the same thing as at, and that's where we get this from. Now, to solve it this way, we need to first calculate the acceleration. Maybe we don't want to do that. Maybe it's not so bad. I anticipate they'll probably have us calculate the acceleration here in a bit. So maybe we should just do it for good measure anyway. It's not too bad, right? Especially since we've got it up here. So it's going 4.4 final minus 2 initial. So those are just the difference in the velocities. The rise, the run is 3 seconds. So it goes from 2 to 4.4 over 3 seconds. So 4.4 minus 2 divided by 3, 0.8. So its acceleration is 0.8 meters per second squared. The time that it was accelerating, right, because we're dealing with sort of this part of the graph, so that's the 3 seconds squared, a half, plus we're going to account for this part of the motion, 2 meters per second times 3 seconds. So 2 meters per second times 3 seconds. Once again, the seconds will cancel. We got meters. Here, the seconds squared will cancel, right? Once we square this term, we'll have seconds squared, canceling out these from acceleration. So meters plus meters is meters. This will give the area for the accelerated part of the motion. And we've already calculated the area and therefore the displacement of the non-accelerated part of the travels. 2 times 3 is 6. Half of 0.8 is 0.4. 0.4 times 9, right? Because 3 squared is 9. So you have to do 0.8 times 5.4 times 9, 3.6. So 6 meters because of this, 3.6 meters because of this. So a total of 9.6 meters due to accelerating for 3 seconds. And then staying at 4.4 meters per second for 2 seconds covers another 8.8. So the total distance traveled is going to be the sum of these two. 8 plus 6 is 14, 18.4 meters. You should get for that. We'll check the mark scheme, make sure you did good on that one. 18.4 meters, keep that in mind for number 1 method. Question goes on to say, show that the acceleration is 0.8 at a time t equals 2 seconds. And so that's taking the slope of that first part of it. Remember how we did it. We said 4.4 minus 2. So that's the final minus the initial over the time. So that was from like at time 3 seconds, we were going 4.4. At time 0, we were going this speed. So you could kind of think about it like v minus u, t2 minus t1. But usually t1 is 0. So we just kind of think about it as v minus u over t. And that's how we got our 0.8. So any kind of working like that, maybe you could find another point besides those endpoints that would show it the same. It says the tension in the wire at time 2 seconds is 240 newtons. Calculate the horizontal component of tension acting on the skier. So let's clear that. So at 2 seconds, this is where we just calculated. We know that the acceleration is 0.8 at that time. There's tension in the wire. The angle is 28 degrees. The tension is 240 newtons. Okay. The horizontal component of tension is going to be this one. And so if we know the hypotenuse and we know the angle, we should be able to use the cosine function because it's the adjacent. So the cosine of 28 degrees is equal to the horizontal component of force over the hypotenuse, which is 240. So cosine of 28 degrees, 0.8829 times 240 newtons gives me 212. So my calculator gives me 211.9, which you might be tempted to say, well, that's 212, but you might also call it 210, right? So, well, how does this rounds up to 212, right? Well, the 2 significant digits, we'd round it down to 210. So maybe about 210 newtons of force. The total resistive force are acting on the skier in the horizontal direction. So here it's like, if the sum of the forces equals mass times acceleration, and we know that it was an 89 kilogram skier that's accelerating at 0.8, you can solve the right side of this by just multiplying. If something's accelerating with mass, the product of those two things gives the net force, the resultant force. Remember, things don't accelerate unless there is a resultant force. There has to be a net force in some direction. Whatever direction the net force is in, that's the direction of acceleration. So obviously the way the skier is moving this way. So right away, we can calculate 89 times 0.8 gives us our net force, 71.2. The forces have to add up to that. If there's a 212 Newton force pulling the skier along, and there's some resistive force opposing it, so we're subtracting that away from the 212 to get a net force of 71. We know that the net force is 71 because that's what's creating this acceleration. So in other words, by multiplying MA, you know what the resultant force is. Then you consider the left side of the equation and say, well, that's vector addition now. You got to add up all the force vectors. What's true about a resistive force vector, R, is that it always opposes the direction of motion. So if we know that the force that's making sort of the person move this way is the horizontal component of force, 212 newtons, 210, something like that. I'll use the 211.9 value. Minus some value R equals 71. So what do we got to do? We got to add R to both sides, and subtract 71. 212 minus 140.9. So you call it, 141, or so it's just about 140 newtons. Right? So we got to take away from our pull force, as it opposes it, to get our net force, which we know has to be equal to the product of mass and acceleration. Good old Newton's second law, even though we start with Newton's first law. They all go hand in hand. The skier is now lifted upwards by a gust of wind. For a few seconds, the skier moves horizontally through the air with the wire at an angle of 45 degrees to the horizontal, as shown. By considering the vertical components of the forces acting on the skier, determine the new tension in the wire when the skier is moving horizontally through the air. The vertical components of the forces acting on the skier. One vertical component that the skier has is their weight. Weight always goes straight down, so that's vertical. And the weight is mg, and the m is 89 kilograms. And let's say, oh, that right there, that looks like well, it looks like Earth right there. Yeah, that's Earth. So that's 9.81 newtons per kilogram. Yeah. I was wondering if this was a Martian skier for a minute, but no, these lines here clearly are Earth lines, right? Everybody can see that. 89 times 9.1. So this skier has a weight of 873.09 newtons here on Earth, which means the downs got to equal the ups, right? Lifted by a gust of wind for a few seconds, the skier moves horizontally, which means there's no net force up or down, right? So if the skier has a weight of 873.09, it used to be the Earth itself was, providing a normal force upward, balancing this. But now all of that force has to be supplied by the upward component of tension, okay? And so now we know we're solving for the new tension in the wire. So that's this, right? What's the tension in this wire? The wire is here. We know the vertical component of this tension is 873.09 newtons because the downs got to equal the ups, right? If there's no acceleration, there's no net force in the y direction. So we know the vertical component is this, same as the weight. And now we've got the side opposite, the hypotenuse. That's the SO in SOHCAHTOA. So the sine of 45 degrees, the function of the angle equals the ratio of sides, the opposite over the hypotenuse, which we're calling T for tension. Multiply both sides by T, divide both sides by the sine of 45, which is 0.707. So it's going to be 873.09 divided by square root of 2 over 2 sine 45, something like that. So divided by I get something that doesn't seem very reasonable. Let me check it again. 873.09 divided by sine of 45 equals. I get a tension of 1, 2, 3, 4. 0.7, so you'd probably just round that to 1,200 newtons of force. And there we've got a good old dynamics calculation. All right, let me go back here. One, that. And here's our mark scheme for this one. So we have correct working on that. Although maybe we didn't round this down. Maybe we left it like 18.4 or something. I got the acceleration correct. They rounded it to the same level of significance we did here. Same thing here. Got this one, 1200. So well done on this one. Good job, everybody.